Okay, so what is Fatou's lemma? It states the following. They have a sequence of functions. So let's assume each of these is measurable. E, of course, is measurable. Now let's assume we have Fn converges to F pointwise almost everywhere on E. So Fn of X converges pointwise to F of X for almost every X in E. Okay. So the conclusion is that this is less than or equal to the lim inf of the integral of the fn's. So proof of Fatou's lemma. A little bit technical, but yeah, it's a clever proof. It's a very clever proof using continuity of measure. Okay. So without loss of generality, assume that we have pointwise convergence on E. And I can do that because well, I just otherwise excise a set of measure 0. So we know this is true for almost all X in E. Excision, excising a set of measure 0. We can assume we have this for all X in E. Okay. So I claim that it's enough to show ETS for enough to show. And I'll go through the details. They're kind of trivial, but that's fine. It's enough to show that the following is true. Okay, the integral over all simple functions, var phi, or whatever this is, I think it's var phi, is less than or equal to the lim inf of these integrals. Whereas usual, this is simple. And is between 0 and F. Okay. So let me call this quantity here star, so I don't have to keep writing it. Yeah, this is by definition. If true, then this integral here is primum of all these. Where these are simple. Okay, so what does that mean? That means that this quantity here is an upper bound for all of these integrals over all these simple functions that are between 0 and F. Let me call this I, this whole set here, I for the set of all these integrals over simple functions. So this is an upper bound, I. Well, soup is the least upper bound. So this is soup of I So we get what we need. And this is important to be able to look at simple functions. Right. So yeah, this is our goal here for all these simple functions. All right, so I divide this up into, well, 3 cases. I'm not even going to call it a case. First, if this is 0, well, then we're done. So what am I doing? Sorry, I'm picking one of these simple functions. I want to look at this integral here. Rather, I want to look at this integral here, where we pick one of these simple functions. If the integral is 0, well, 0 is less than or equal to something non-negative. It's 0. So there's nothing to do. All right, so let's assume the integral is not 0. So easy case is the integral is 0. So we're going to show that the integral also is sorry. So this is going to be infinity. This doesn't make sense. So basically, we're going to show both sides are infinity in this case. Okay, yeah, this is not too bad. So if this is true, then I can clearly pick some subset of E that has infinite measure and where this here is positive. The particular, it's a simple function, so it can only take on a finite number of numbers. Finite number of non-negative numbers. So we can pick we can pick this to be positive. And if we can't find E infinity, and of course this is measurable, E infinity. We can't find A and E infinity, then, well, clearly, then this integral is finite. Okay. Yeah, if we can't find a positive A where the simple function is A on some set of infinite measure, then the function is positive on only sets of finite measure. And henceforth, the integral is finite. So kind of trivial there. Okay, so yeah, so we define some clever sets and use continuity of measure. So we know that F is the limit of Fn as n goes to infinity. So we don't want to strictly work with A. We want to work with anything smaller than A, but so A over 2 works. So let's define An in this following way. So this is admittedly a little tough to motivate. It's just kind of, you go back and like, okay, well, this works, but why would I choose this in the first place? A little hard to describe, but So I want to settle x where fk of x is bigger or equal to a over 2 for all k bigger or equal to a. Okay, so clearly this is ascending. If x is an an, then clearly x is an an plus 1. Because being an an means fk of x is bigger or equal to a over 2 for all k bigger or equal to n. Well, if it's true for all bigger or equal to n, it's true for all bigger or equal to n plus 1. It's kind of trivial. So these are definitely ascending. Maybe just make this a little neater. But okay, much nicer. All right, so by continuity of measure, we have that this limit is the measure of the union of the ans. Okay. Now, how does this help us? Okay, well, A is var phi of x. And that's less than or equal to f of x on E. Sorry, on E infinity. So what does this tell me? Well, this is the limit. Yeah, sorry. So f of x, sorry, is the limit as n goes to infinity of fn of x. And well, f of x is bigger or equal to a. So that means this limit here, and this is kind of what's important, this limit here is bigger or equal to a. So definition of limit, there exists n where for bigger than n, then fk of x is bigger or equal to a over 2. That implies x is in an. And the point is, as x varies, well, you might have different n's. Well, just take the union. So that means x is in an. Okay, so in other words, E infinity is a subset of this union. This goes in the exact direction I want, because this has infinite measure. So infinity is going to be the measure of the sets. That's less than or equal to the measure of the union. I don't per se care about that, but we had by continuity of measure, this is equal to the limit, and that's what I want. I want this limit to be to have infinite measure. Okay. All right. Sorry. There is no en, it's an. Okay, so how do we get yeah, so how do we get that this limit, well, this is infinity. So actually we're gonna show, sorry, we're actually gonna show the limit is infinity. Not necessarily I mean the limit is a limit, but we'll show that the limit is infinity. Should have made that clear a little uh clear before. And now we're gonna use Chebyshev's inequality. Okay, so in particular, so I'll write this. This is kind of obvious. Um, yeah, so an is a subset of this here. Why is that? It's pretty obvious. So if x is an an, where's the definition? If x is an an, then this is true for all k bigger or equal to n. In particular, it's true for n. N is bigger or equal to n. So if x is an an, then fn of x is bigger or equal to a over 2. Okay? So if x is an an, then fn of x is bigger or equal to a over 2. Okay. All right, so what does this say? This says that this is less than or equal to, by Chebyshev's inequality, um 2 over a, and a could be really small, so this could be huge, but that doesn't matter. That's fine. So it's e integral fn. Right, so infinity is equal to this limit. Okay, well, that's less than or equal to 2 over a times this limit here. Okay. So the conclusion is, well, this is positive. Okay, so multiply by a over 2 on both sides. We get exactly what we want. The limit fn is equal to infinity. So sorry, the lim inf the lim inf of the integral being infinity is equivalent to the limit of the integral is infinity. So they're the same thing, really. If we actually think about the definition of limits. Okay. So yeah, we've proved. If you have any doubts, double check that lim inf of this integral is infinity is the same thing as the limit itself being infinity. What I want to do is the second case. So the second case, remember, case 2 is that this integral here is finite. And so remember, in general, we're showing that this integral here is less than or equal to the lim inf as n goes to infinity, and if this is true on E. And this is simple. This is a simple function. So we did the case, the integral of var phi is infinite. Sorry, brain fart there. Yeah, so we did the case where the integral is infinite. In that case, we showed that the limit on the right-hand side is infinity also, which means the lim inf is infinity. So, or rather, the limit as n goes to infinity of the integral of the fn's is infinite, which is the same thing as saying the lim inf as n goes to infinity is infinite. So yeah, this is simple. Okay, so yeah. So how do we handle this case, which is definitely a little more complicated? It's a somewhat similar, quite clever argument that we're going to use. Okay. Right. Okay, so yeah, we're assuming this. So clearly this is finite. Oh, okay. So what I need to do first is excise the zero set. So in particular, let E0 be the inverse image of 0. So a set of all x and e where the var phi, my simple function, is 0. Okay, and if I do that, and let's say e prime is e take away e0, well, clearly this also is finite. And this equals whoops, sorry. So this is finite, and this is going to be equal to e prime. Well, e is e prime union e0. Okay, well, my function is 0 on e0. In particular, the integral over e prime is also finite, and my function is positive on e prime. It's a simple function on e prime. Positive simple function on e prime. All right, so let's say epsilon is positive. And let me set this here to be y1 through, for lack of anything better to use, let's say yl, or some natural number L. And here everything is positive. Because we've excised the 0 set. So additionally, set M to be the max, big M to be the max of all these. And let's set epsilon prime to be epsilon over m plus this integral. Okay, which is well, it's positive. The denominator is positive. Everything's finite, it's a real number. So yeah. Okay, so yeah, so kind of like we did before, a little harder to even motivate why we're doing this, but we'll see in a minute. It's a really clever argument here. Not very difficult, but very clever. So here I want to use continuity of measure going the other way. In particular, what I mean is I want to get nested sets and use continuity of measure. All right. So yeah, let's say En is a set of x and E prime, where Fk of x is less than or equal to 1 minus epsilon prime times phi of x, or var phi of x, whatever it is, for some k bigger or equal to n. All right, so something to note that I'll use in a second. Clearly, this being infinity implies this integral is infinity. In particular, the integral is bigger or equal to the minimum of all these. Times this measure. So that means this, and remember this is positive because all the y's are positive. That means this has to have finite measure. In particular, why do I care? Well, in particular, E1 is a subset of E prime, and so E1 has finite measure. And I should point out, we'll use this in a little bit. We don't really need it now, but let me not use purple. It doesn't it blends in too much. I'll use yellow here. So you can actually, I mean, trivially you can write, or not trivially, but very easily you can write this is going to be k equals n to infinity. And in this case, it's clearly nested. These sets are getting smaller and smaller and smaller. And again, I'm just writing this to indicate why it's clear that these are nested sets. They're getting smaller and smaller and smaller. But we will use this, what's in the yellow, in a minute. And in a little bit. So, okay, so by continuity of measure, we have the limit is the measure of the intersection. Okay. Now I claim, the limit is 0, and I'm going to prove the limit is 0 by proving that this is empty. Okay, well, let's see why this is true. If X is in this intersection, and I'll leave some 511 details for you to do. So first, well, first of all, X, if X is in this intersection, that's an E prime. So this, not stating a whole lot here. We're at E prime, so this is positive. This is a simple function less than or equal to f of x. This is the limit. And the point here is if we're in all of the ENs, then no matter how far into the sequence we are, we can always find a large K where fk of x is less than or equal to 1 minus epsilon prime phi of x. Or rather, for any n whatsoever, we can always find a K bigger or equal to n where fk of x is less than or equal to 1 minus epsilon prime phi of x. So that means this is less than or equal to 1 minus epsilon prime. I'm going to do that. Phi of x. Again, if you have any doubts, prove this. This is where we're using x as in the intersection. Again, what are we saying? What does it mean to be in the intersection? For any n whatsoever, we can find a k larger where fk of x is less than or equal to 1 minus epsilon prime phi of x. Okay. And because the limit as k goes to infinity is equal to f of x, there's a little easy basic analysis argument says this is true. Okay. If you have any doubts, I would prove it yourself. Okay, but this is absurd if you think about it. Why? That's kind of the point. We're trying to prove that this is empty. So in particular, let me divide by, well, I'll just write this out. So let me divide out by phi of x, and I will second. Yeah, sorry. For some reason I thought I had 0 here when I divide out. So what does that mean? 1 is less than or equal to 1 minus epsilon prime. So minus epsilon prime, or rather 0, is less than or equal to. This is clearly absurd. 0 is less than or equal to minus epsilon prime. This is absurd. So in other words, picking x in this intersection gives us a contradiction. Okay, and again, why do I care? I want this limit to be 0. Right. And by continuity of measure, the limit is the measure of the intersection, which is the measure of the empty set, which is 0. So we get the limit is 0. Okay. So we're actually almost done. Pick big N. Where little n bigger or equal to big N gives me that the measure En is less than epsilon prime. Okay, so now I want to look at the complement of En. Remember, we had En is this union here that allows me to complement it complements very easily. Sorry, it's the union, not the intersection. It's the union. Yeah, so take the complement in E prime. This is going to be the intersection. So it's the intersection of these complements. So if it's not less than or equal to, it is bigger than. As simple as that. Okay. And in particular, well, x and E prime take away E n implies F. Well, in particular, this says that x is in the k equals yeah, sorry. X is in the k equals n set because n is bigger or equal to n. This is the intersection where k, is n plus 1, n plus 2, et cetera. So in particular, k equals n is part of the intersection. So Fn of x, this is really crucial. Okay, so this in green. So I'm going to need this, and I'm going to need this. And I also need this, but it's a little less, it's much more trivial than the other ones. So I need those 3 facts in green in a minute. I'll go back in a second. Okay, so yeah, what's my original goal? Need to get a lower bound on these integrals. That's kind of the goal. So this here, bigger or equal to integrating over E prime, take away E n. Okay, on E prime, take away E n. This is true. So this is bigger than, or bigger or equal to, doesn't matter. 1 minus epsilon prime times the integral of 1 minus, sorry, integral of the simple function, bar phi. Okay, now I'm going to write it as integral over E prime minus the integral over En. Okay, yeah, so okay, 1 second to check something really quickly. Bear with me a second. Yeah. Okay, so this is equal to this integral minus this integral here. Right, but this here, of course, is less than 1. Okay, so this is going to be bigger or equal to, because this is less than 1. So the whole thing without the minus is less than the integral of en fn. Minus makes it bigger or equal to. Okay, and this whole thing here is going to be less than or equal to m times the measure of en. So they should be the simple function, not fn. I don't know why I wrote that. Sorry about that. Right, so remember the simple function is less than or equal to m. Because m is the max of the range of the simple function on E prime. Yeah, so it's less than or equal to m times the measure of En. And that is less than or equal to well, m E prime minus, so it's bigger or equal to. So what is this equal? This is going to be equal to phi of r phi, whatever. Integral of r phi minus epsilon prime m plus this integral. And this is bigger or equal to, remember, epsilon prime was set to be epsilon over this is what epsilon prime was set to be. So this is going to be integral phi minus epsilon. Again, epsilon prime was set to be epsilon over this whole thing here, which is right here. So less than that, minus makes it bigger, equal to. Okay, so what is the conclusion? Little n bigger than big N implies the integral E n is bigger or equal to integral E prime phi minus epsilon. Okay. So in other words, this here, what I'm going to circle in whatever color this is going to be a lower bound for all of these integrals for n bigger or equal to big N. That's the point. The inf is the greatest lower bound. So this inf is bigger or equal to this integral here. Okay. Right. So, but so as n goes to infinity, big N goes to infinity. We're taking the infimum over less and less and less indexes, less and less and less integers. So the infimum increases because it's we're looking at less and less and less stuff. We're looking at less and less and less of these integrals as big N goes to infinity. So in other words, as a function of big N, so I'll write it like this. Just repeating like a basic fact of really limits. So sorry, this is increasing. This is increasing. So in particular, the lim inf I'll use n little n. So this is bigger or equal to this inf here, which we concluded is bigger or equal to E prime minus epsilon. Yeah. Here again, we use that the inf is the greatest lower bound. All these integrals for n bigger or equal to big N. All right. Yeah, and epsilon is arbitrary. And actually, really, these integrals, these could be infinity. We don't care at all. It's increasing. There's a subset of non-negative numbers. Well, of course, remember E prime is simply E with the zero set excised. So this was arbitrary. We get exactly what we want. The lim. So again, not a hard proof, but like a really, really clever proof. I definitely would not be able to just sit down and kind of think to my piece out, flesh out like the way the idea to prove this. I would not think of doing it this way in a million years. It's really clever proof. Yeah, a long proof, but yeah, hopefully it's made sense. If not, just let me know. And yeah, that's that. All right, so long, take care. Bye-bye.